All right, so first things first, hopefully everybody has seen the announcement. So the problem that most people had the most difficulty with was the stack question.
Number 5?
I think that's number 5. That is number 5. So, so I'm offering you a do-over opportunity on that, if you like. And there's instructions in that announcement, but there's a PDF, it's a one-page version of the quiz, it's just question 5. Print that out, fill it in, put your name on top, staple it to your original midterm, and turn it back into me by, I think I said Thursday morning. And you can drop it off in class or in my office or the front office, they can leave it in my mailbox, and I will regrade that.
I just wrote down the wrong number. I said 10 in my brain and wrote 2 because it started with T.
Yeah.
My brain works really stupidly.
Why not 3? You didn't even have to know stacks to do that, right? Because I gave you the code for it. But I think the fact that I said it was a stack actually threw people off, because a lot of people started doing things like thinking when you pop a number, the value in the array becomes unknown. And if you look at the code, when you pop a number, all you're doing is changing the stack pointer and returning a value. You don't touch the values in the array itself, so those values don't change. So that was usually a lot of points, and I thought it was going to be a quick 20 points, right? So I put it in there as kind of an add-on to your grade, but then I ended up just taking off, at least half those points in many cases. So,
at least for me, I went through it and I was doing that problem, and then I noticed the code up there at the top, and I was like, oh wait, I should read that, and that's why I thought maybe you made a typo because it didn't mesh with how I was thinking.
Right.
And so I was like, oh, and then you walk through the code line by line, and it just it's a simple problem. But the
probably next time I just won't use the word stack.
Or make the code a little bit more bold.
Or I just won't say stack. I'll say here's some routines, and I'll call them like Barney and Betty or something instead of pushing the file. And if you know what a stack is, you might recognize it, and that might be able to speed you up. But I might do that next time. Yeah, or make the text bold. So I went through the midterm in detail yesterday, and that class is recorded. So I'd rather not take a whole lot of class time today to go through it, but I can make a few comments, but certainly if you have any questions on it, this is a good time to ask. Common issues I saw, so when we're, yeah, go ahead.
There's one thing I keep getting when it comes to pointers and everything, and hopefully you can do just a quick overview on this one really quick, but the arrow versus the dot.
Yes.
I keep, even when I'm writing the program, I kind of just take a 50-50 gamble sometimes. Because if I'm trying to call a pointer from something that's already a pointer, is that an arrow or a dot? If I'm calling a string out of a pointer element, like when we had the struct node star was just, or struct data star was like a capital D data or whatever it was. Is that a dot or an arrow? And how do I remember?
Okay, cool. So struct stuff. Here's your field 1, car star field 2, struct stuff field 3, struct, I can't do that. Let's do struct stuff pointer field 3, and we'll just leave it at that. All right, so there's a structure. It has 3 pieces to it, 3 fields: an integer, a car star, and a struct stuff star. All right, so here's some possibilities. Struct stuff var. So var is a variable I'm declaring, and it is a struct stuff. When you have a variable that is a structure, you access the fields with a period. So I can do something like var dot field 1 equals 12. That's legal. I can do something like var dot field 2 equals malloc 20. That's legal, because this is returning a pointer. It would be illegal to say var arrow field 1.
What would that call? Would that call a pointer?
So var arrow means take a thing pointed to by var and pick off field 1. It's just like a dot, but it says, but first dereference that variable to the left. Take the thing that it points to, and then say dot field. And since var is not a pointer, it's actually a struct stuff, the value at this is probably, it's probably an illegal memory address. So I'll probably say false if I try to use an arrow, but in fact the compiler will probably stop me.
So it's not a matter of what you're trying to call as a field of the structure, it's a matter of whether the structure itself is a pointer or not.
Exactly.
So if I'm trying to call, say, field 2, which is obviously already a pointer, and it was, say, a struct stuff star var, like a
Like
pointer.
field 3.
Yeah.
Mhm.
So let's go ahead and lay out struct stuff, or struct stuff star pointer, PTR.
Mhm.
And then how would you call field 2 from it?
So struct stuff star,
Or,
let's call it PTR.
sure, whatever, that works.
All right, so if var is a struct stuff, I could say var dot PTR. That is a pointer to a struct stuff.
Okay.
Okay, if I want to access, say, field 1 from this, I could do this. Because this thing is a pointer.
So then the biggest difference then is you want to use a dot after something that's actually the structure and an arrow after a pointer to a structure.
Exactly.
Okay, so that's nothing to do with what you're trying to call from it.
Right.
Got it, cool, thank you.
Did everybody get that? That's a good way to describe it. And as we move forward, more and more of what we're going to be doing is going to involve pointers to structures. So we'll see the arrows more and the dots less.
All this is doing just randomly.
Yeah, that's what a lot of people do. The problem is sometimes that works.
And if you use the var plus, and that goes by the number of bytes into the structure, right?
You mean
Like if I'm calling a string, field 2 plus 1 would be elements, or would be the second character in the,
yes,
yeah.
and I avoid doing that if possible.
Always better to use the square brackets.
Yeah. If it's really an array, use the square brackets to index it, because that will take care of adding the right amount.
Interesting. The C primer book, and Scott in his class made a point to say that it's almost the exact same thing as just using the bracket notation?
Yes,
It is.
Okay. All right.
but the brackets really scream out like element 0, element 1, element 2, and late at night when you're looking at your code and you say, well, I added 4 to the pointer, why isn't it getting me to the next element?
Does that go by bytes then?
It goes by the size of the thing that it's pointing to. So if you add 1 to an integer pointer, it actually adds 4 to the pointer.
So it adds one integer,
Yes.
or one size of integer, okay.
And that just, seeing bracket 1, we're used to saying, okay, that's going to be the next element no matter how big it is.
Okay.
Saying x equals x plus 1, we kind of expect it to add 1 to the value of x. And in that one case, it doesn't. It adds 4 to the value of x.
Right, because,
Or maybe you're on a machine where your integers are 2 bytes and it adds 2. And it's a little easier to get into trouble with that. That's the only reason I kind of shy away from it.
gotcha, thank you.
But yeah, it does the same thing. interesting thing on linked lists, I think only one person, maybe two, used a temporary variable in writing the code for this. And you don't need a temporary variable, but it can make life a little easier when you're working with these kinds of things. So here was a list. Here was our sentinel node. Here was a 6. Here was a 4. And here was a 1. Let's go to 0. And what points to what? And it's really easy to be off by 1 here. So LL is the address of this sentinel node. Right, if I were to print LL, I'd get some big hexadecimal number with 7s and Fs, and it's a location in memory. But if I say LL arrow next, remember that's the thing that LL points to, and we want the next field. Right, and these blocks are set up. Our structure looks like data and next. So the thing that LL points to is this, and the next field is this block right here. So this block is LL arrow next. Well, same thing. LL arrow next points to this block. If I were to take the thing that LL arrow next points to, and pick off the next field, that's this block right here. And this is a long version of LL arrow next, arrow next. So this block right here is L next, next. And if you continue, this block over here will be LL arrow next, arrow next, arrow next. And it's easy to be off by 1, right? If you think that this is LL next, or you think that this is LL next, right? So LL points here, this block, this piece of the structure is LL next, which points to this node. This piece of the structure is LL next, which points to this node, and so on. So our print statement printed LL next data and LL next data. Well, if this is LL next, then this is LL next data. And this is LL next arrow next. And this is just LL next data. And if you like, it may help to break this into parentheses. Right, this node is LL arrow next. And so this is the data part, and this is the next part. And this node is LL next. And this is the data part, and this is the next part. So if you get a good picture like that, and you're totally clear on it, then these questions are pretty straightforward. So the first one, print LL next to data, is this piece, which is a 4, and then print LL next data, that's a 6. And that one, you just had to nail this down perfectly and hope that it was right. And if you got one of those right, I only took off 2 points.
I'm not quite following you. So the first one that you wrote down is LL next, which is the first node, right?
LL arrow next is the contents of this piece of the sentinel.
Okay, so if it's the contents of that piece of the sentinel, and then you're looking for the data, so the next arrow is to a data. So when I don't understand how that's the data of the next, of a different node,
so
instead of the data of that
this
one.
data value right here would be LL arrow data. Do you agree with that?
I think this is an easier way to label them.
Yeah.
Right, because LL is pointing here, take the thing it points to, pick off the data field. This is LL data. This is LL arrow next.
Okay.
Okay, so
Next one would be L next data.
yeah,
L
let's
next
I
data.
think of it like layers.
Yeah.
let's try it like this. Temp equals LL arrow next. Suppose I make that assignment. So temp is the value that's stored in here, right?
Right.
Which is the address of this node, because that's what this field does, it points to the next node.
Okay.
So temp is pointing to this node. So this node is again temp arrow data, and this is temp arrow next.
So one portion of that is going to be ahead of another portion if you're looking at it linearly.
Mm-hmm. Yeah,
Okay,
the data is probably stored first.
okay.
So if you believe this, if this is LL pointing to here, this is LL data, this is LL arrow next, if we just name this temp, then it's exactly the same setup. This is temp arrow data, this is temp arrow next. But if we use the fact that this is what temp is, and we plug it in here, this is LL arrow next, arrow data. And this is LL arrow next, arrow next. And you can chain them together like that. And this can probably be something GDB helps with, because GDB understands this notation. And if you actually look at the value of LL, right, put that down on paper, draw a box next to it and say this is the address of this node, and then look at LL arrow next, and look at your memory, you'll see that whatever value LL next has, that's what's stored in this block of memory. And if you look at what's at that address, you'll see an integer followed by another address, and so on. But for these other questions where we're trying to delete a node and insert a node, we don't have to be fluent in this LL arrow next, arrow next, arrow next business. We can do this a lot more easily if we use some temporary variables. So for example, I don't really want to erase it. Part B said we want to delete this last node, and we're not allowed to use loops or conditionals. But we could do something like this, temp, so struct node, star temp. Temp equals LL arrow next. And if I know that this is LL, and this is LL arrow next, temp is equal to the value in this piece of the structure, which means now temp is pointing to my 6. And then if I say again temp equals temp arrow next, this is what temp points to. Take that block, that's what the arrow says, and look at the next field. That's the address of this. So that second statement is going to change temp to point right here. And now I want to delete the node that this node is pointing to, because that's the last node. So I can just say free temp arrow next, and then temp arrow next equals null. So when I free it, that releases this from the memory, puts it back in the memory pool, and then I set this to null. That's my delete. And the order matters, because if I do these in a different order, if the first thing I do is temp arrow next equals null, I change this and this becomes null. And then I say free temp arrow next, I'm going to try to free null, and I'm going to get an error. So we want to make sure we use this address before we change it.
So, I mean, I managed to do part B in just 2 lines of code, but I was trying, when I was writing it, to figure out what the return value of free is, because if it returns null, it'd be really handy to just say, LL next, or free LL next, and it would return it, or
Right.
assign it to the LL next.
Yeah, I think free returns void, I'm not sure.
I'm gonna have to look it up, because it'd be really handy to simple it down to one line.
I'm pretty sure I saw that one.
Yeah.
Is it void? Okay.
Well, and free doesn't actually change the pointer that you pass to it, so it can still point to an old address.
Yeah, well, that's what I'm saying is if it did return null or had some way of doing it, like, then you'd be able to just call it and it would change the next to null.
Mm-hmm.
But I don't know.
Yeah,
That's
yeah.
what I'd do if I was writing a release function for it, but you didn't write
If
function.
you wanted to, you could just wrap it with something that does return null.
Good point,
That
good
way you
point.
can
That's
say
true.
equals release.
Yeah.
But then you have pointer equals something pointer.
So, two
Yes,
lines
so
code
just to
probably works.
confirm, you do want to free the node first before setting the new null, because otherwise you wouldn't be able to find that one.
Right. I mean, we could take this and we could set it to another temporary variable.
Yeah.
And then we could change this to null, and then we could use that temporary variable to free it. That's fine.
Yeah, 'cause that's
So
what
you
I
can
did.
free it in any order you want,
Yeah,
but
I
if
said null
we,
first, then free.
if we destroy that address, we've got to have it saved somewhere or be done with it. So yeah, the 1-line or the 2-line version is right, so LL, arrow next, arrow next, arrow next. So we free that, and then we LL, arrow next, arrow next, arrow next equals null. But I have to have like a really quiet room and a good night's sleep to really sort of be absolutely comfortable with that kind of thing. I prefer just sort of marching it through.
Really, I found the 2-liner easier, because I was just able to follow my pencil, I was like,
Yeah, yeah.
right there, cool.
I'm always afraid I'm going to be off by 1.
Well, if I wanted to really sleep well, I really had to fight just making an all cases conditional loop. Just find the one you want to release
Right,
and
right.
release it.
Yeah. Want to sleep really well, I'll feel like Archie's true. That's what we're doing now. All right, and then doubly linked list. Not too much trouble with that either. So here you were actually writing a function, you've got a previous and a next to deal with. But the whole setup is basically as follows. So here's our sentinel. So we've got data, previous, and next. That's our basic node structure. So this is called list. And we don't care what this data is, but here's some data 1, here's some data 2. And it's doubly linked, so we have back pointers. So this points back to D1. Technically in a doubly linked list, I would make this back pointer null. Just like when you go forward, if you get to a null, you know there's nothing after that. If you're going backwards and you get to a null, you know there's nothing before it. But if you had it pointing back to the list, I gave you credit for that, because we didn't spend a lot of time on doubly linked lists. So the goal is to insert. So we want to go from here to the following. and we've got a new node. So what do we have to do? We have to create a new node. So call malloc the size of struct node. Set your new node's data to be equal to new. And then we need to join it into this list. So we need to make the following adjustments. We need our list to point to our new node. We need our new node to point to D1. We need D1's back pointer to point to our new node, and we need new's back pointer to point to probably null. So we need something like this, new arrow previous equals null. So that'll put a null in there. We need D1's previous to point back to our new node. So the way we get to D1 is list arrow next gets us to this node, and then the arrow previous gets us to this. So list arrow next, arrow previous, and that should be equal to new. So this now points back to new. And then our new node should point forward to what used to be the node after the sentinel. So new arrow next equals, and it should be D1, which is list arrow next. So that causes this to point to here. And then we need our sentinel to point to our new node. So list arrow next equals new. And that breaks this link. And points to new. And we did new previous equals. I switched my forward and backward. We did new previous equals null. List next previous equals new. New next equals list next, and list next equals new. So now here's our list, points to this node, points to D1, points to D2 and continues. D2 points back to D1, D1 points back to new, and new points back to null. Again, I could not recite this in under 10 seconds, even if you offered me $1 million. Right? I don't have this committed to memory. I probably never will. But if you know how you're trying to manipulate these, right, you can synthesize this based on what you want to happen with your nodes. So this is what you want to understand. The other thing is, this has the potential to cause a sig fault. Because if our list is originally empty, all it has is a sentinel node, list arrow next could be null. In which case, when I try to say, take the thing that that points to and look at the previous, that'll sig fault. Only one student caught that. Yeah. So, but I didn't.
I forgot to assign the previous of the.
Yeah. All right. Hashes, I went through that on the tape yesterday, but make sure you understand how to do hashes, right? I mean, you need to do this by Friday for PA3. So if you lost points and it's not like, oh, I know what I did wrong, I definitely ask.
I just forgot how to do a module.
Yeah, so a lot of people did. So make sure that's working for you. And then the stack is your redo opportunity, so I'm not going to go over that. And then let's just run through the short answer ones really quickly. So abstract definition of a queue, right? Initialize, is it empty, is it full, insert, remove. It's your interface to the code, and it's devoid of any knowledge of what's going on underneath the hood, right? So this line of code, C here, is not using that interface. It's interacting with a variable called head. It's assuming that we want to increment it and roll it over when it hits 1,000, so we seem to know that the queue is in an array of 1,000 elements. And it's a circular queue, and it's using all these details of how the queue is implemented. And you know, you might implement a queue with a linked list, and there is no array, and there is no plus plus, and there's no %1000 anywhere in the code that implements that queue, and my line C would make absolutely no sense. So C would be the answer there. Segfault potential, so X is an integer, Y is the address of that integer, and then I say, show me the value of Y. Nothing illegal with that. Every variable has an address. Even if I've never initialized X, it still has an address, and that address is fixed when I start the program. So Y will be some location in memory, and I'm saying, show me what that location is, and that's perfectly legal. In B, though, I'm saying X is a pointer to an integer, but I haven't said what the value of X is, where it's pointing. And then I try to set Y equal to whatever X is pointing to. And if X has a value of negative 17 million, that's not a valid memory address. And when I say Y equals star X, that would say called in that case. So B can definitely get you in trouble. C is just printing the sum of two integers as an integer, nothing wrong with that. And D is saying X is an integer, Y is a pointer to an integer, and I set Y equal to X's address. And even if X does not have a value, Y is pointing to the place in memory where X is stored. And when I say star Y, that says, show me the value at that location in memory. So this is no different from just saying printf X. And we don't know what value it will print, but it shouldn't segfault. They're just printing the contents of memory. So B is the outlier there that could potentially cause a segfault. Allocating space for an array of 125 elements of type struct big. So malloc 125 times size of struct big would be the typical way to do it. If you did struct big variable bracket 125, I gave you credit, but that wasn't what I was looking for. But technically that works. Valgrind detects memory leaks. So do other things as well. I mean, you could say a printer is a tool for detecting memory leaks, because you can use a printer to print out your code and look at it. But I was looking for the tool that's most specifically used for memory leaks, and that's Valgrind. Compiling code for debugging. Right, that would be sufficient. That creates an a.out with debug symbols. But if you also add on an output file, that's fine. A disturbingly large number of people did something like this. Right? And this says I want to compile a program called main, and I want you to take the output and put it in something called main.c. And it's just written gibberish into main.c, or maybe just zeroed it out, and your source code is good. And so hopefully you got backups.
I think GCC would complain over that, wouldn't it? It'd say something about, if you'd have an error before you even got to the point of outputting a binary.
You know, if you do that, maybe it would actually compile it. I haven't tried it.
Yeah, so I think if you do that, it would work. But I'm pretty sure in the past, maybe like back in 120, I've done it the first way, and it stopped me.
Yeah.
I bet that wouldn't even work, because when you...
I'll try it at the break.
When you give it an out file that is like a binary, right, it doesn't actually, it just creates it in memory, the object file, and then it goes through those steps.
Yeah. I'll bet I can find a way to get in trouble with that. If the directory contains a make file, what command do you type to build it? Make. And allocate 10 bytes of data and assign it to a variable named pointer, so just pointer equals malloc 10. Don't do 10 times size of car star, because I'm asking for 10 bytes, not 10 characters. And then check to see if pointer is equal to null. If it is, you know you were out of memory. And a fairly common thing is to do something like if null equals malloc 10, return error. Otherwise, pointer equals malloc 10. I've seen this a few times on the test and a few times other places. The problem with this is, and it can be fairly subtle, when you do this, you're allocating 10 bytes of memory. If you run out of memory here, you will successfully say we ran out of memory. But if this succeeds, this is going to allocate another 10 bytes. And this could be the one that runs out of memory. So you've allocated 10 bytes, you've done nothing with them, so they're lost, it's a memory leak. And now you're allocating a 10, you still need to know if pointer is null. So functions often have side effects.
If you put
And
PTR equals 9,
yes.
10 there.
Right. So be cognizant of side effects of functions when you use them, because that pops up in different places. All right, so let's do a 5-minute break, and then let's talk about binary trees.